Thank you all for coming here bright and early on a Sunday morning, and hopefully I'll stay awake for the entire presentation. A little early for me, but that's okay. That's why they have Starbucks in the So I'm going to talk about risk-targeted ground motions, which probably many of you don't know what that term is. Hopefully you will know what that term means by the end of this presentation, and with a specific focus on the central and eastern U.S. That's the CEUS, what this session is about. So first I'd like to recognize our team. There was quite a team for putting this together. And so these motions were recently put together and balloted, meaning voted on by AASHTO, the code writing body for bridge design in the U.S. And we had the USGS, the Geological Survey. The lead consultant was Majeski and Masters, and then there were a number of other both consultants and university folks that worked on this. And you can see Mervyn, for example, here was part of the team, and Federal Highways was also part of the team. So this now has been adopted and just a couple of weeks ago published by AASHTO. So we're now in the implementation phase. So before I get into the presentation in depth, I want to just set the stage with some definitions here. One is hazard, which we have used hazard as our design basis for earthquake ground motion for many years. Hazards mean what the ground can do essentially by itself, even though we're characterizing that with a single degree of freedom oscillator with a response spectrum, but that's an elastic response. Fragility, the new term we're going to put in, and I will say as a designer, I hate this term. I don't know who came up with it. They weren't a structural engineer. I don't believe. Anything but fragile would be a better term. But anyway, fragility has as a meaning as a structural response damage function. In other words, what's the probability that spalling would occur? What's the likelihood that we would have yielding or bar buckling, or what we're going to talk about today is full collapse, I mean loss of gravity support. And then when you integrate or put hazard and fragility together, we can get risk. And so that's a consequence of hazard combined with fragility that leads to the potential for collapse of a structure. And it's risk targeting, where we're trying to move from hazard to looking at probabilities of collapse. That is this last term. And now the risk-targeted ground motions will be our new seismic input for design of structure. The building industry has already moved to this, and the bridge industry is moving now to this. And so the design process is the same. We're changing the input, but the process stays the same. So there's minimal changes for designers in the trenches doing their daily job. So the motivation for this, first in AASHTO, we adopted new displacement-based design guidelines in the 2007, and at that time, the best map we had from USGS was 2002 hazard map, and that has stayed the basis of AASHTO for many years. It's time to update, so there's been a lot of improvements that USGS has done in terms of looking at seismic sources. Mervyn just mentioned this earthquake in North Carolina. Historically, one of the great ways you got on the earthquake design map was to have an earthquake. So I'll bet that USGS is changing some of what they're doing in that North Carolina, South Carolina, Virginia area. There have been improvement in site factors and soil effects. Some of the older data we've been using we found to be unconservative. We're moving to multi-period accelerations instead of just 3 design accelerations that then form a pretty simplistic response spectra. This was to take into account things like basin effects that affect certain period ranges. That's the last bullet here. And then there were new attenuation relationships. An attenuation relationship is what happens from where the earthquake happens to where your site is located. How does that motion propagate through the Earth's crust to get to your site? And so there's been a lot of work done to improve those relationships. And in this case, in the central and eastern U.S., they've changed motions dramatically, in fact, reduced them, which is a good thing. And then some states, following on motivation, some states have abandoned the AASHTO maps just simply because they were very old, 2002, and come up with their own maps or adopted newer USGS maps, which is a state's prerogative to do. But then we've also seen this notion and the capability now of risk targeting versus using uniform hazard. And so that was another motivation. And then this is also a move back to a national standard for ground motion. Following on motivations here, I mentioned the next generation of attenuation. They resulted in dramatic reductions in the hazard-based design motions in the eastern U.S. And on the surface, that would seem a good thing, but I'll show you a complication with that in a few slides. And so because of this, we wanted to address this complication that we'll get to. Risk is, because of the complication, risk is unequal across the country due to variations in the hazard. In a single return period, we've been designing for many years, let's say a 1,000-year return period or 7% chance of exceedance in 75 years. But just designing for that one thing doesn't address what happens if we get a different earthquake, because the Earth doesn't do the same thing twice, typically. And so there wasn't any explicit consideration of what might happen if a larger event occurs. And then, as I mentioned, the building side, ASCE 7, had moved to risk targeting for these same reasons. So if we look at response spectra, and I apologize, I've got some graphs. I know it's 8 o'clock in the morning. Well, you're all engineers, so hopefully you'll hang with me with the graphics here. So this is for Los Angeles. So it's a West Coast site. And you can see, see if I can get the laser screen. So here you can see the dashed lines are the existing 2002 AASHTO uniform hazard. So these very simplistic response spectra. And then in the new 2018, this is what we're moving to in terms of the basis for hazard from U.S. Geologic Survey, is the solid line. So you can see how this variation by 1 over t, this is the spectral acceleration versus period plot. You see how we've got increased motions in this range of about 1 to 3 seconds. Well, we have a lot of bridges in 1 to 3 second range, so this is an important change. And this has happened for various site classes. So over here we see B, C, D, and E are different site classes going from B is relatively firm to E, relatively loose soil. And when we look at the same thing for Charleston, South Carolina, now we're in the eastern U.S. site, see the existing 2002 hazard at the 1,000-year design ground motion. And now you see for site class E, for example, quite a drop. Here's the solid line is their new 2018 ground motion. If we look at a D site, that's the purple. Here's the 2002, and a bit of a drop there relative to the earlier ground motion. So these differences now we need to address. And so let me show you something else that's behind this. You could kind of fish it out of those curves. This shows it more directly. Is that if we look at the probability of exceedance in, say, probability of exceedance in 75 years on the ordinate over here, and the ground motion acceleration on the x-axis here, then what you see in this particular case, we've picked 2 cities, Portland, Oregon, which is on the west coast, Charleston on the east coast, and at the design ground motion, 7% in 75 years, or 1,000-year return period, they have exactly the same spectral acceleration at 1 second. which would be what sets the design requirements. But then if you look at more rare earthquakes, say at 3%, now you see Charleston has a much higher acceleration, maybe about 0.45 G, versus Portland, which is about 0.35 G. You see quite an increase here in the east, and this is characteristic of the east, that as you go to longer return periods, you see much higher accelerations than you do at 1,000-year ground motion. And we've known this for years. We originally were designed for 500 years, and the 2,500-year earthquake in Charleston, for example, is about 6 times as large in terms of spectral acceleration as the 500-year motion. It's a little less for the 1,000, but still it's quite a difference. So this characteristic difference is why, one of the main reasons why we're moving to risk-targeted ground motions, to pick this difference up. And so historic earthquakes in the U.S., 1886 in South Carolina, 1811, 1812 in the New Madrid area, much larger earthquakes than the 1,000-year design event in those areas. So in risk targeting, what we're trying to do is adjust to say we have a similar probability of failure, in this case, incipient collapse. Haven't collapsed yet, but we're right at the threshold of it, probabilistically. And this is similar to the development of LRFD for the design codes for gravity loads. And it's an attempt to bring the design process into more uniform reliability across the country instead of using one return period. And it's because of this non-uniformity is the main reason we're moving to risk targeting. Now, to do this, we need to use, again, what I call the fragility function. And so we're going to use, just like we use a notional truck, not an actual truck for design, we're going to use a notional fragility function. And we're going to use one fragility function for the entire country. And this, a lot of people have really gotten wrapped around the axle with this, but it's simply a first step to try to put everything on a similar basis in terms of risk versus hazard. And so the fragility function looks like this graph shown to the right here, where we have a probability of incipient collapse and then spectral acceleration. You could use spectral displacement as well. And this is a cumulative curve, and there are only 2 points that are required. The conditional probability of collapse at the design point, which is where we're doing our design work, and that's taken as 5%. And then the log normal distribution with a standard deviation of 0.6, which sets the shape of the curve. And this has been calibrated back to some ACI work that's been done on column collapse from a number of years ago. And so what we're trying to do then is set this curve up so that we adjust it so that we get a consistent probability of collapse in our design. And one thing you will note here is that at 5% at the map ground motion doesn't mean that you'll have no collapse at the design point. There's a small probability you could have collapse there. All this said, mathematically, I want to take a step back and look at a quote that Tom Pauley, who co-authored a book with Bob Park in 1975, is one of the best reinforced concrete structures book ever written. And in this 1993 Mallet Milne lecture in London, he said the design engineer's goal should be to make the structure have tolerance with respect to the inevitable crudeness of predicting earthquake-imposed displacement. I want you to focus on that inevitable crudeness. This is not an exact science. And so we do a lot of things very precisely with numbers, but we should remember that it's not as precise on the ground as you might think it is on a piece of paper. Now, again, it's 8 o'clock in the morning. I'm showing you an integral. I apologize. The point here is we have to combine fragility and hazard. We do this with this integral. You don't have to worry about it because USGS does this for you. And if you develop a site-specific hazard response spectra, they have a tool online that then you can have them integrate your hazard so you don't have to do this. This is very similar to LRFD, which you, I think, probably have all heard of. And there you're not doing this integration either, but that's what's under the hood. So the important thing is that at risk targeting, we vary the ground motion to achieve a target risk level, incipient probability of collapse. Now let's look at this back with the Portland-Charleston comparison. So if we look at this and actually perform the integration, and this shows area under the curve. It's not the area under this curve, but that's just that. We're just showing that to distinguish the two integrations. But if we took straight away this integration with a constant fragility with the two hazards, we find that in Portland, the risk of collapse in 75 years would be about 2.8%. In Charleston, it would be 3.5%. So they're not the same. This illustrates the difference between the East and the West in this regard. Now, if we wanted to make them equal at 2.8%, for example, just an example here, we've got to increase the design acceleration for Charleston up to about 0.25 G from about 0.21 G. So it's not a huge increase for this particular case, but that's what has to happen in order to get the, quote, risk equal between the two sites. Now, what the group has selected as the target risk is 1.5% probability of collapse in 75 years. And this calculation, this integration is done, we're looking at now 22 points for a response spectrum. Each point has this integration done for it. Again, why you should thank USGS and your federal dollars for paying for this integration so you don't have to do it. This example just shows the 1 second period and in terms of spectral displacement. And for Memphis, what was required, Memphis is in the New Madrid seismic zone in the mid-America, and we had to increase the design acceleration by 22% here to get the risk in Memphis to 1.5%. So we're going from a 1,000-year return period, we had to increase by 22% at this particular period to get to a target incipient probability of collapse of 1.5%. And then one other thing I'll draw your attention to, and the curves here are the same as before, the hazard and then the fragility, and then the yellow or orange curves are the actual contributions to the probability of collapse, and then the cumulative. And what I want you to see is that over 90% of the contribution is above the design point. So this is where if you're designing something, you don't want to just get to your target ground motion and then have everything break and come apart. You need some tolerance for the uncertainty of the design displacements that Tom Pauly talked about. So in summary, the AASHTO seismic provisions now that have been adopted and are being used, maps are not included. Maps for 22 points, it just would inundate you with paper. So and nobody's really doing this anyway now. It's all numerical. You go to a database, you get this stuff, you put it in a spreadsheet or whatever your program you're using. And then they have also included additional site classes. So we had A, B, C, D, and E. F is a special site. They've now included halfway in between those. So a BC, a CD, a DE. So those are helpful in terms of site characterization. And then we only have shear wave velocity. So if you're using standard blow counts, standard penetration test for your site characterization, to adjust those to shear wave velocity. You do need, because of the 22 points, you'll need new methods for calculating the corner periods. When you're going through the design code, there's a provision for that. And there's an appendix that's added to the guide specifications for seismic design that go through a lot of background information similar to what I'm giving you today. So let's look at a couple of examples here, again, going back to Charleston with response spectra, spectral acceleration versus period. This is the risk-targeted versus the 2018, so the newest USGS. And you can see how here, again, the hazard is the dashed line and the risk targeting is a solid line. You can see how here, for the poorer sites, that's D and E, the motions increase and increase quite a bit in this range that's important for bridge design. If we look at this relative to the 2002 map and what AASHTO had been using up through 2020, you see that the 2020, or same as 2002, are given by these dashed lines. You see quite a bit of drop here for several of the poorer sites. And then there's actually a little bit of increase for sites B and C, again in Charleston. If we go to a Mid-America site, this is St. Louis, you see a similar trend for the ground motions, quite a bit of drop from the uniform hazard from 2002. And then Boston, where we are now, a really large drop of all the ground motions. And this is primarily driven, as I said, by this next generation of attenuation factors that USGS is using to propagate their ground motions to your site. And so then one of the things that might be occurring to you is, what does this do with regard to, say, return period? So if we look at the return period on the vertical axis and spectral period of those 22 points on the horizontal, and we look at, this is a class DE boundary site and then a class E site. And then the colors are, red is the western U.S., blue is the Intermountain West, so that's basically the Rocky Mountains, and then the green is the central and eastern U.S. And so for the most part, you see that in the west, things stay right around or just above 1,000. You see these two lines taken off very steeply in the west. Those are, say, Seattle and Portland, which are in the Cascadia subduction zone. So long period motions in subduction zones are important. You see that here now with the increase in the effective return period that each of these points are being designed for. But if we look at the green, you see that now in the east, for both of these, many of the sites are moved up into the, say, 1,400 to 1,500 year range, which is appropriate because the longer return period earthquakes, say 2,500 year earthquakes in the east, are much larger than the 1,000 year. And in fact, as Ty Stokes will talk about later, in South Carolina they're already using 2,500 year earthquake. So then, just got 2 slides here to wrap up. And we've got in the guide specifications, there's an appendix, provides a lot of different information here on how to do, how this calculation is done, what it means, references to the USGS, that sort of thing. We don't need to go into all the geotechnical specifics today, but there's information there for you geotechnically. And then perhaps one of the more important slides, you might want to take a picture of this or write this down, or you can find it online here. These are the websites to get your risk-targeted ground motion response spectra by latitude, longitude, and site class. And then if you do site-specific work, where that calculator is. So, important stuff. This is where you find information so you don't have to do the integration.
And now our next speaker is